Hello students, Mr. Courtney here. In this video I'm talking about measurements and calculations. We're going to look at scientific notation, uncertainty in measurements, and significant figures. So these are our objectives. We're going to talk about a measurement, define a measurement, look at how we write numbers in scientific notation, discuss and evaluate accuracy, precision, talk about uncertainty in measurement, how uncertainty arises, and we're going to explain why measurements must be reported to correct number of significant figures. And we're going to also perform calculations with significant figures. So what is a measurement? So in science, measurements are fundamental to experimental sciences. Therefore, it is important to be able to make measurements and decide whether a measurement is correct. So in terms of that, what do we mean? So measurement is a quantitative observation. That means it has a number and a unit, where the number indicates the size or the amount and the unit tells you the scale being used. So here we have two measurements of length. We have 1 in centimeter and we have 1 in millimeter. They both have the same number, so they have the same size, but the unit or the scales are different. The first one is measured in centimeter and the second one is measured in millimeter. So we have centimeter here and we measure in millimeter. Just as if we take several other measurements like height, your age, body temperature. But we can also express these in different units also. So your height could be given in feet or inches. Your body temperature could be given in degrees Celsius or degree Fahrenheit. So in chemistry, you will encounter very large or very small numbers. Now, writing these large and small numbers can be very cumbersome. We can take chemical quantities and express them or manipulate them using scientific conventions and mathematical procedures, just like we can use scientific notation. And that makes it easier to work with these numbers. So what is scientific notation then? It is an easy way to write very large and very small numbers. Makes these numbers easier to work with. So for example, we have these two numbers. It would be very hard to write these numbers like that, whereas we can write them in scientific notation. So when we talk about scientific notation, it consists of two parts. It has a coefficient and an exponential part. An exponential part is a base 10. So some coefficient multiplied by 10 to some exponent. Now your exponent is an integer. It must be an integer. That means it must be a positive or a negative whole number. And your exponential part, as I said before, it's times 10 to some exponent. And your coefficient is the number at the front. So we have to make that connection with math. The number in front, the variable in math, is what we call the coefficient. So in here, if you consider this, the exponential part, to be a variable, then this is the number in front of it. So this is our coefficient. Now the coefficient is equal to or greater than 1 but less than 10. So that means you can have a value anywhere from 1 to 9.9 or 9.999 as long as you don't cross 10. Now that means also that you can only have one digit before the decimal point. Now our exponent depends on two things. The number of places the decimal point is moved, that gives us the value or the number, and the direction in which the decimal point is moved. It tells us if it's positive or negative. So what does a positive exponent tell us? It tells us that the decimal was moved to the left, as we see here. So that means we should get a positive exponent here because the decimal was moved to the left. And how many times to multiply by 10. So each time we move the decimal to the left, it means we have to multiply by 10. Now if we have a negative exponent, that means the decimal was moved to the right, as we've done here. We moved it 2, 3, 4 places to the right. And that tells us how many times we need to divide by 10. So if we have these numbers, it means we have one digit before the decimal point. So the first one will be 9.3 by 10 to the 7. Because we moved it to the left, it's positive. And we moved it 7 times. And the second one, we get 1.67 by 10 to the negative 4. Because we moved it to the right 4 times. So that gives us negative 4. So when we're multiplying and dividing numbers in scientific notation, we do it the same way as if you would do indices. That is, you multiply the coefficients and add the exponents. So if we have these two numbers here, we take our our coefficients, which are 3 and 2, multiply them, then we take our times 10, which is our base, then we add the exponents, which would be 4 plus 2. So that gives us 6 by 10 to the 6. In this example, we have 2.1 as one of our coefficients and 4.0 as the other coefficient. So we multiply these two, 2.1 times 4.0. Then we have times 10, which is our base. Then we have 3 plus negative 7. So that gives us 8.4 by 10 to the negative 4. Now, when we do division, division is the opposite of multiplication. So this time now we're going to divide the coefficients and subtract the exponents. So in this example, our coefficients are 3.0 and 6.0. So we divide them, we minus our exponents, and then we get to this point here, here, where we don't have any digit before the decimal point. So that is incorrect scientific notation. So we need to move the decimal point to the right. Whenever we move it to the right, we decrease our exponent. So exponent is going to get smaller. Since we moved it one place to the right, then our exponent must decrease by 1. So it becomes 2. And we get 5.0 by 10 to the negative 2. In terms of addition and subtraction, what we need to do is that we need to ensure that the exponents are the same. And that is, we need to get decimal points aligned before adding or subtracting. So we have these two numbers. Here we can see we have an exponent of 10 to the 3 and an exponent of 10 to the 2. So they're not the same. So what we're going to do is that we're going to convert our smaller exponent to the larger exponent. So we're going to move the decimal point to the left. So we get 5.4 by 10 to the 3 plus 0.8 by 10 to the 3. Remember, if we move the decimal point to the left, we're going to increase our exponent. So we go from 2 to 3. So now we can add 5.4 and 0.8. That gives us 6.2 by 10 to the 3. And that would be our answer. Now, in chemistry, or in the lab, when you do labs in chemistry, you will need to make reliable measurements. Now, your measurements should be both correct and reliable, or as we say, they should be both accurate and precise. Now, to many people, these two words seem to mean the same thing, but accuracy and precision are very different. When you take a measurement, the reliability of the measurement is based on the accuracy of the measurement and the precision of the instrument. And here we're focusing on the words accuracy and precision. When we talk about accuracy, we're looking at how close the measurements are to the actual or true value, to the accepted value. And then the precision means how close are a series of measurements to each other. How close are these measurements to each other? Are the measurements consistent? Are they reproducible? So that means if you do it over and over again, you should be getting about the same value. That means it's consistent. Now, let's decide here if the marksman was very accurate, very precise, or both. Now, in 1. Now, look at the closeness to the bullseye. This indicates a high degree of accuracy. The closeness to one another indicates high precision. So that means there's good accuracy and good precision. In this one, precision is high because of the closeness of the grouping. That's a high level of reproducibility. But the results are inaccurate because they're far away from the true or accepted value, or in this case, from the bullseye. Poor accuracy, but good precision. In this one, the shots land far from one another and far from the bullseye. The results are both inaccurate and imprecise. So poor accuracy, poor precision. Now, if you have this instrument, we have two different scales and we're measuring the mass of the same object. Here we can see two different values. So what determines the accuracy and precision of an instrument? The accuracy and precision of an instrument is determined by the size of the increment. What is an increment, you may ask? An increment is the smallest unit an instrument can measure. So if we look at the one on the left, it can only measure up to the 10th place, so 1 decimal place. The one on the right can measure up to 3 decimal places. So this is going to give us a more precise value or more accurate value of the mass. So smaller the increment, the greater the accuracy and precision. So this results in this value being more precise. Now also, 12.7 is not the same as 12.700. This is the reading we get on the balance. We do not know what digits come after here. And as we can see, there's a 3 here. So if we were to take this and measure it as 12.7, we cannot assume that the other 2 digits are zeros. If we want to give it to 3 decimal places, we have to use an instrument that would actually give us the 3 decimal places. The size of the container is not related to the precision of the instrument. Only the size of the increment is. So only the size of the increment affects the precision of the instrument. So as we can see, we have the same volume of liquid in both containers. In this case here, we have a 25 milliliter gradiated cylinder, and we have a 50 milliliter beaker. When we look at the value here, the volume here, the volume seems to be approximately 20 milliliters. And if we look at our increment, we go from 10 to 20. So we're increasing by 10. But when we look at this one here, we get a different value. We see that it's not that close to 20. We actually see we go from the major markings go from 15 to 20. So that's a difference of 5. And there are 10 markings from 15 to 20. So we take the major markings, the difference in the major markings, which is 5, divided by the number of markings in between, 10. So we see that each one represents 0.5. So if we were to read the volume now, this would be 19.5. That's 19. And that's approximately 18.5 milliliters. So here we see we get 2 different values based on the container we use. So this value here would be more precise because we have a smaller increment than in this beaker here, because we have a larger increment. Now, when we talk about uncertainty in measurement, all measurements have some degree of uncertainty. And that uncertainty is dependent on the precision of the instrument, the person taking the measurement, and also sometimes the conditions of the measurement can also affect the outcome. What kind of conditions are you taking those measurements under? When you take a measurement, any digit that must be estimated is termed uncertain. So you're not sure it is that value, but you're estimating it. So it's an instrument. If we were to read the volume at the bottom of the meniscus here, we get the volume as 20.15. So we estimate it to be 20.15. So we know this is 20 and this is 0.1. This is 20.2, and it's somewhere between 20.1 and 20.2. And we're going to estimate that that last digit is 5. We're estimating that it's halfway in between these two values. So we get 20.15. So the 20.1 is our certain digit. Those digits are certain. The uncertain digit is the 5. So what is the length of this nail? If we were to measure the length of this nail, as we can see here, so different people gave different measurements. But when we look at it closer, we see that we have is actually 28.5. Now all these, and those in red here, shows that these values, the last digit was uncertain. These were our estimated digits, so they're uncertain. So significant figures are the numbers recorded in a measurement. So it's the certain numbers and the uncertain number, or your first uncertain number. Now, if it's significant, it does not mean that it's certain. As we see here, the certain numbers plus the first uncertain number is what we call the significant numbers. So any numbers recorded in a measurement. Now, measurements must always be recorded or reported to the correct number of significant figures, because many times the calculated answers depend on the number of significant figures in the values used in the calculations. So if we know how many significant figures we use in the calculations, then we can determine how many significant figures we should have in our measurement. So when we look at a measurement, how can you determine which digits are significant? So To determine that, we need to look at the rules for determining significant figures, and you need to be familiar with the following rules, as you'll be using them very often from now on. First rule, all non-zero digits are significant. So all we do here is that we count how many non-zero digits we have. In 42.7 we have 3, 0.473 we have 3, 1.74 we have 3. So each of these measurements has 3 significant figures. Rule number 2, leading zeros, that is those that precedes non-zero digits, are not significant. They only act as placeholders. So in point 0.0081, these zeros, these 3 zeros are not significant. They're acting as placeholders. This is acting as a placeholder. These are acting as placeholders. So we count only our non-zero digits. In all cases here we have 2. Now you can eliminate placeholding values by writing the measurements in scientific notation. And here we see when we write these numbers in scientific notation, we can see clearly the 2 significant digits or significant figures. Third rule, captive zeros, that is those between non-zero digits, are significant. So since these 2 zeros are in between 2 non-zero digits, then they are significant. So that gives us 4. This 0 is between 2 non-zero digits, so it's significant. We also have 4, and this 0 is also between 2 non-zero digits. That gives us 4 significant figures each. Trailing zeros, that is those to the right of non-zero digits, are only significant if a decimal point is present. So these zeros are significant because a decimal point is present. This 0 is significant because it's trailing to the right of a non-zero digit because a decimal point is present. And these 3 are significant because of this decimal point being present. So in each case here we have 4 significant figures. Trailing zeros again to the right are not significant if a decimal point is not present. So if you don't have a decimal point present, then they are not significant. No, the decimal point here is implied but not present. So these zeros serve as placeholders to show the magnitude of the number. So in this case we have 1 significant figure here, sorry, and in this case we have 4 significant figures because the zeros are not significant. Now, if the zeros are known measured values, then they would be significant. So for example, if you were to measure a length of 300 meters or 7,000 meters, then these zeros are significant. So again, write the value in scientific notation. That makes it clear that the zeros are significant. So if you write it 3.00, then we have 2 significant figures. 7.000 by 10 to the 3, we have 4 significant figures. Numbers that are counted are exactly defined quantities. They have unlimited number of significant figures. So 30 students in a classroom, that is a counted value. So it would have an unlimited number of significant figures. 60 minutes in 1 hour, that is a defined quantity. So each of these would have unlimited number of significant figures. Now let's look at the rules for rounding. So if we want to round the number, first we need to decide how many significant figures the answer should have. The number of significant figures in the answer depends on the given measurements and on the mathematical operation used to obtain the answer. So if we want to round these up to 3 significant figures, if the digit following the last digit to be retained is greater than 5, then the last digit should be increased by 1. So we go 42.68. We want 3 significant figures. So that's 426. The number after 6, the third significant digit, is greater than 5. So we need to increase it by 1. So that's 42.7. If it's less than 5, we have 17.3. That's our third significant digit. The number after the digit we want is less than 5. So that third significant figure stays the same. So we get 17.3. Let's look at if we have to round these numbers here. In 1, we have 314.721 meters. We want to round it off to 4 decimal places. So that's those in green would be our significant digits, the digits that we want. Now after the 7, the number after the 7 is 2, so that's less than 5. So we keep the 7 the same value. So that's 314.7 meters. We also want our answers in scientific notation. So we're going to have to move the decimal point 2 places to the left. So that's 1, 2. So that gives us 3.147 by 10 to the 2 meters. In the second one, we want 2 significant digits. So the 1, 7 are our 2 significant digits in green. The number after the 7 in green is 7, so it's greater than 5. So that means that second significant digit needs to increase by 1. So we get 0.0018. And we need to move our decimal point from here to between the 1 and the 8. So that's we're going to move it 1, 2, 3. And since we're moving to the right, we're going to have a negative exponent. So that's 1.8 by 10 to the 3 meters. And on the third one, we had 8792 meters. We wanted to 2 decimal places. So the 8 and the 7 are significant. The number after our significant digit, second significant digit, is greater than 5. So that 7 needs to increase by 1 to 8. But we need to keep the same value of the number. So we add zeros. Because remember, the zeros are placeholders. So we need to add these 2 zeros. These show our 2 significant digits. But remember to show clearly what we want. And in this case, we're also asked to write it in scientific notation. We go 8.8 by 10 to the 3 meters. Now, when we do addition and subtraction of numbers, and we're using significant figures, we're going to run the answer to the same number of decimal places as the measurement with the least number of decimal places. What does that really mean? It means you cannot have more decimal places than the least number of decimal places you have in your calculation. So your answer cannot have more decimal places than the least number of decimal places you have in your calculation. Let's look at an example. So we have these 2 examples. So we're going to add these. Now when we look at this one, this number only has, the second number only had 1 decimal place. So that means our answer cannot be more precise than to 1 decimal place. So we're going to add these numbers as normal, but we're only going to go to 1 decimal place. When we get 369.7, the number after the 7 is 6. So that means we need to increase it by 1, 369.8 meters. And the second one, and if we write it in scientific notation, is 3.698 by 10 to the 2. And the second one, we're subtracting. Again, our second number has only 2 decimal places. This one has 3. So our answer cannot have more than 2 decimal places. We subtract as normal, get our answer, and then we round off. So we stop at the 8. The number after the 8 is greater than 5, so the 8 has to increase by 1 because we have the 8 is our second decimal place. So 46.29, or if you write it in scientific notation, 4.629 by 10 to the 1 meter. If we look at multiplication and division of significant figures, we're going to round the answer to the same number of significant figures as the measurement with the least number of significant figures. So in this case, we're looking for the least number of significant figures in our numbers we're using, and then our answer cannot have more than that. So that's the number of significant figures we're going to have. So we have 7.55 by 0.34. In this 7.55, we have 3 significant figures. Here we have 2 significant figures. So this limits how many significant figures we have. Our answer can only be given to 2 significant figures. So we multiply our numbers, we get 2, 5, 6, 7. We can only have 2 significant figures, so that's 2.6. Because this is 2.5. Our second 2 significant digits will be 2.5. Since the number after the second significant digit is greater than 5, that means that digit needs to increase by 1, so we get 2.6. If we're dividing, Here we have 5 significant digits. That's 1, 2, 3, 4, 5, because they're all non-zero. And then we have 1, 2. So answer must be given to 2 significant figures. So we perform our multiplication. We get 0.29176. The number after the second significant digit is less than 5. So we do not change the second significant digit. It remains the same. So that's 0.29 meters. Okay, this takes us to the end of this lesson over measurement, scientific notation, accuracy, precision, or we say uncertainty in measurement, and significant figures. So until the next time, I'm out. Blessings.